Okay, let us proceed with the second case where when these two masses are at the same level horizontally. Okay, as we have initial conditions also, and we will have later the final condition. This final condition, this is initial conditions. And for the case of Newton's second law of motion, of this motion of motions, the first approach, we will use the same formulas, because we just check the direction of rotations of this disk and the direction of rotations of sloping of these two masses. They are moving downwards in a clockwise direction of this rotating disk. Therefore, the final velocity of the system will be the same as when it is 3 meters apart. Therefore, when you follow this first approach closely, you can find that it is the same. You can get the same speed, that is 3.36 approximate meter per second. Okay, as this first approach, I explained it very well in first video. And now let us proceed this second case, when these two masses rest in the same level with a principle of conservation of energy. Okay, this is initial conditions, this is final conditions. Initially they are in the same level, these two masses, and when the rotations takes place, the mass 1 moves up a distance s, and this mass 2 moves down the distance negative s here, as you can see. Therefore, we will have that we have to apply this principle of conservation of mechanical energy. It is from initial conditions to final condition as usual, and this is also a isolating system. Okay, from initial conditions, we'll have the terms as you can see here. I just try to mark it with a red, black, and purple, and therefore for rotations, for potential of mass 1, rotation for disk, translation kinetic energy for mass 1, potential for mass 2, and here is translation for mass 2, kinetic energy for mass 2. These terms, as you can see, red becomes 0 also, and this black becomes 0 at initial, as the coordinate is 0, 0. There is no translation, there is no potential energy, there is no kinetic energy, there is no rotational energy. Therefore, the left terms, all of these terms become 0. As you can see here, the green also becomes 0. Now, the final conditions is when this mass 1 displaced from 0, coordinate to 0, positive s, and this mass 2 displaced from 0, coordinate to this 0, negative s coordinate. Therefore, for potential energy of mass 1 is for positive directions, and this m2, it is for negative direction potential energy below 0, coordinate, and this translational kinetic energy for mass 2 and for mass 1 is there as usual. V is equal to final velocity, which is equal to common V, the velocity of the system, the whole system. Okay, and this final rotational kinetic energy is just there through the center of gravity, or the center of masses, because this is only rotational kinetic energy without any translational motions, because this is rotating through the axis, through the center. Okay, therefore, here we will take all the masses in a lefty side after equal sign, and we remain with kinetic energy in right side. Okay, then we substitute this moment of inertia through the center of gravity of the disk, which is a half, and then we'll have these terms here. Okay, and this V through the center of this disk is the same as through the center of masses of M1 and M2, which is the same as through the system, the whole system, as indicated earlier in earlier case. Okay, we multiply with 4 in both this in each terms, then we will have V final here as equal to this right terms, and now if we want to find our R times W square, which is equal to this V square, then we just want to connect it with W square from the third equation of rotational motion, and then we will have this equations. After substituting this W and divided by R square, we multiply, we divide with R square both sides, and then we substitute this value of W square, because W square is equal to V square divided by R square. Okay, and for this angular acceleration, as usual, we come from the third equation of rotational motion, then we substitute from W square, which is final, then we will have the equations as you can see here below. And therefore, remember the moment of inertia through the center of the disk is a half mass times r square. Then we substitute here. Okay, don't forget it. We make we take these two out in such a way that here is equal to m times r square, as we have this r that we take it, we just open this brackets and multiply to this mass and this bracket masses m1 and m2, as you can see here. Therefore, we just want to get the moment of formula where we have moment of inertia through the center of gravity. Okay, then in order to get the linear acceleration, we multiply with r r of the disk. So this r is the same as this capital R, sorry for writing the small r. It is the same capital R. Very sorry, same capital R. Okay, then we will have a linear acceleration, as you can see here below. Thanks for watching. Please like, share, comment. Don't forget to subscribe this YouTube channel for more video like this one. Remember, this answer will be the same for velocity, that is 3.36 approximately meter per second, and for this case, when they are in the same level, also it will be the same.